Hello, everyone. Welcome to the next lecture of op amps. In the last lecture, we talked about non-inverting configuration of the amplifiers, and we started, um, in particular, one of the applications, the difference amplifiers. We discussed how we can make our difference amplifier from the op amp, and we also saw the condition under which we can reject the common mode signals using the difference amplifier. So we're gonna so let me quickly show you that thing again. This is where we left. We had so what I'm doing is I am just drawing a difference amplifier circuit. So V1 and V2 are the two input signals that we are interested in taking the difference. R1, R2 are the resistances here, R3 is here, R4 is here, and V0 is here. Then we saw that to reject common mode signal between inputs, we found a condition that R2 over R1 should be equals to R4 over R3. So we found a condition in which if we can make R2 equals to R2 and R1 equals to R3, okay, so we can make, if we can satisfy this condition, then the output voltage will reject the common mode signal, and our output voltage V0 will be equals to R2 over R1, which represents the gain factor, and V2 minus V1, which represents the difference of the signals of the inputs that we have applied at the input of the amplifier. So we also saw this, that for gain G to be higher, right? So if we want our gain to be higher, then the input resistance, which is R1, should be lower, right? So if over here I want my output to be higher, of course I want my R1 to be lower. But we also know that we need higher input resistance, in this case R1, to prevent the signal loss. So this is where we kind of stopped in the last lecture, that in this difference amplifier, we're just taking the difference of the two inputs, and this represents the gain factor. In order for the gain to be higher, our resistance R1 should be lower. R1, which represents the input resistance to this amplifier, it needs, however, we also know from our earlier analysis of the amplifiers that our input resistance should be higher to prevent any signal loss due to the coupling of the input to the amplifier. So what we suggested as a solution is, we said, okay, as a solution, we need a instrumentation amplifier, and this is what we are going to discuss today. And essentially what we do in this instrumentation amplifier, all we do is we will use non-inverting configuration voltage followers for both inputs, right? So if you remember that we talked about this early, that if our voltages are reasonably okay, we can use voltage follower circuits to provide a higher input resistance, while the gain can be unity or does not need to be nominally very high. So instrumentation amplifier exploits that concept. Okay, so let's make the instrumentation amplifier, and we are going to quickly analyze that circuit as well. Instrumentation amplifier. Okay. All right, amplifier is a little bigger, so right. So we had two inputs, V1 and V2, and we are going to connect non-inverting voltage follower circuits to both the inputs. So for example, look over here how I am making the circuit. I think this should be helpful for you as well. V1 negative, or negative positive, V2. So this is the ground here. And all right. Excuse me. All right, so this is the instrumentation amplifier. Let me label the resistances: R1, R2, R1, R3, R4, R4. All right. Okay, now look closely over here. So we have connected both the inputs here, this V1 and this V2, to non-inverting configurations. Normally, as you may have realized that by in all the previous lectures, I always draw the op-amp as this negative and then positive. Right over here, I kind of draw it in the other way just for the simplicity for showing the circuit. Otherwise, we can, by convention, we usually draw it like this. Drawing it like this is okay as well. All right, so we have a V1 and V2 both connecting to the non-inverting terminal, and this is a non-inverting configuration, right? And these we have a R1 resistor that is connected to the inverting input, and we have a R2 resistor connected to the feedback. We have seen this thing many times before by now. This is a non-inverting configuration of an amplifier. And what is the gain value of this amplifier? It is usually 1 plus R2 over R1. Right? So the output of this, and this G is usually V naught over VI, where VI is the input that is applied and V naught is the output, right? So now I am going to, let's say the output of this is, the output of this, let's call it as a VA, and output of this, let's call it as VB. Right? So the VA will be equals to V1 1 plus R2 over R1. And this configuration is exactly the same. So it will be equals to V2 into 1 plus R2 over R1. Now let's assume that these VA and the VB are the two voltages that are coming to this network, right? That are coming to this network, to the circuit. What is the circuit? If you look closely, this is our regular difference amplifier. I can also show you in the previous lecture, right over here. So this is our regular where two voltages comes at the inputs. We have two resistors in series with them, and then we have one resistor in the non-inverting terminal in the T network configuration, and the other resistor is with the inverting terminal. It's in the feedback loop. So we have exactly the same situation over here, where we have these four resistances, R3, two R3s and two R4s, and two input voltages are coming in. So this is a regular difference amplifier. All right, so what will be the output will be? So the output will be, if I go back here, right, if we will keep these conditions the same and we have use the same conditions, then the output will be R2 over R1 multiplied by V2 minus V1. So this is our V0. So our output will be R4 over R3 multiplied by VB minus VA. So these are the two input voltages that are coming in. So it will be VB minus VA. And these are the two resistances we have. So it will be R4 over R3. So now we can put down the values of VA and VB. R4 over R3 into what is VB? VB is V2, 1 plus R2 over R1 minus V1, 1 plus R2 over R1. We can take 1 plus R2 over R1 common. So it will be R4 over R3, 1 plus R2 over R1 into V2 minus V1. Right. So this is the output of the instrumentation amplifier. So in order to design the instrumentation amplifier, we have to select these resistance values. We have an R2, R1, R4, and R3. Sorry. And then we have and this is a difference amplifier, which is taking the differential input signal or subtracting the two inputs applied at the instrumentation amplifier. Also, it is rejecting all the common mode signals because of this condition or because of these same resistances that we are applying over here. This output can also be rewritten as R4 over R3, 1 plus R2 over R1, and you can call it as a VID. VID is a differential voltage, output voltage that we get out of the instrumentation amplifier. All right. All right, so now we are moving to the so this is we are done with the applications of the non-inverting configuration as well. I think so the last topics that are remaining in this chapter are the frequency responses of an op-amp. Sorry. So this is what we are going to discuss now. Frequency response of an op-amp 741 IC. Right, so the op-amp comes in this IC chips, and one of the most commonly used part number of that IC is 741. All right, so now we are going to look at the frequency response of an op-amp. All right, so open loop gain of a real op-amp is not infinite but decreases with frequency. Right. So initially we assume that the open loop gain of the op-amp is infinite, right? But we realized that in some of the previous discussions as well, that usually it is very, very high. It is not, of course, it is not infinite, but it's usually very, very extremely high. Now we will see that even that is not true at all the frequencies. it is extremely high at a zero frequency, and then it decreases over the range of the frequencies. So we are going to draw the typical frequency response of the op amp as well. All right, so example. So here's a typical frequency response of a typical 741 IC. So let me draw this. So this is in decibels, mod of A, and this is in hertz. Right. Sorry. This is 100, 0. And this difference is 3 dB. So I'm going to explain that in a second. Let me. Alright, so this is a typical frequency response of op amp IC. On the x-axis we have frequency in hertz, and on the y-axis we have a magnitude response, mod of A, right, which is 20 log of the open loop gain of the amplifier. Right, so at 10 hertz, so at at zero frequency, our gain of the amplifier is 100 decibels, and as we are increasing the frequency, the amplifier response is decreasing. We also saw that whenever there is a 3 decibel decrease is usually the cutoff frequency that we initially defined. We are gonna redefine it again over here in more detail. But interestingly, that you can see that over a very small range of frequencies, for example, in this case, just from 0 to almost 10 hertz, the magnitude response remains same or within 3 decibels. Right after 10 hertz, it starts to decrease by a factor of 20 decibels per decade, right? Which we discussed that it's a 20 decibels decrease per every 10 times the increase in frequency. So if you look closely at this frequency response looks a lot like a low-pass filter with 10 hertz as a cutoff frequency. So why is that? So we are going to actually define a couple of other parameters as well. I'm going to call this as a frequency B, FB, and I'm going to call this as a frequency FT. I'm going to come back to this, what is FB and FT over here are. All right, so a few quick things about this plot around this discussion is, right, so this is a low pass, this behaves like a low pass filter. The frequency response of the open loop gain of a op amp IC. And why is that? Because although we did not talk about what is internally present in the op amp, except that there's a bunch of transistors, almost 20 of them, and there's a capacitor. So what that capacitor is doing essentially, that is turning it into this low pass response right there. is a capacitor in op-amp IC whose purpose is to make it into a low pass response. There is one more thing that I just want to introduce. We will not go into the details of it, and that is called as frequency compensation. So changing, just introducing the term over here, changing the frequency response of op-amps is called frequency compensation. This makes it more stable as opposed to oscillatory. Right, so the things that we learned over here is that this looks like a low pass response. Why? Because there's a capacitor in the op-amp IC, and then we can select the capacitor's different values to get the desired frequency response. So why we are interested in changing this frequency responses? So the reason for that is, so one, this process is known as this fine tuning of this frequency response of the op-amp. This process is known as frequency compensation. So why we are interested in frequency compensation is just to develop more stable circuits rather than the oscillatory response of the of our electronic circuits. So beyond that, I just wanted to introduce a term here. We will not go into the details of how we do that. However, in chapter number 11 of the book, it's sufficiently in detail written over there, where they also discuss the internal structure of an op-amp. So once you know that, you will know how you can better fine-tune your circuits in terms of more stability rather than the oscillatory responses. All right, so let's define, let's look at again the frequency response again. I again want to characterize this FB thing, which is the cutoff frequency, right? So we we talked about our FB cutoff frequency previously as well, right? So this frequency is the frequency in terms of a low pass filter, below which our magnitude response will remain the same or within 3 decibels. If it would have been a high pass response, it would be above this frequency, the magnitude response should remain within 3 decibels, right? So in terms of a bandwidth, so we can again define the bandwidth. The range of frequencies over which the gain of the amplifier remains within 3 decibels is called amplifier bandwidth. Right, for example, over here I can see that the amplifier bandwidth over here is from 0 to 10 hertz. All right. So let's look at that in slightly more detail. Let me actually, all right. So this FB over here, is also known as, I have already introduced all of these terms, so I'm just redefining or rewriting these terms. This is also known as a 3 dB frequency. It is also known as a cutoff frequency. Sometimes it is also known as a corner frequency. Right, so this frequency at which the magnitude response will fall below the 3 decibels is called as a cutoff frequency, a 3 dB frequency, or a corner frequency. Sometimes also known as a break or breakout frequency as well. Let's look more at the frequency response in more detail, especially at 0. What is the magnitude response at omega equals to 0? So let's find that out. Alright, so I'm interested in finding the value. So let's define gain at omega equals to 0. Let's call it as A naught. So it will be a DC gain. Right, so this DC gain will be at omega equals to 0. So let's find that out. So we know that mod of A naught equals 100 decibels here, right? Going back to the plot, this is 100 decibels here. Right, so it should be something 20 log of A naught. So I'm interested in finding out this value A naught. Right, so if you take an inverse log and you will find out this value, you will realize that the value of the A naught comes out to be 10 to the 5. Right, because 20 log of 10 to the 5 is 100 decibels. Now you can realize over here that the gain of the amplifier is extremely higher. In an ideal world, this should have been the same for the entire range of frequencies, but then due to the presence of a capacitor in the low pass response, this gain will remain to be similar for only a very small bandwidth, beyond which, or up till a specific cutoff frequency, beyond which it will start to decrease by 20 decibels per decade. Right, okay. So our A naught is 10 to the 5, very, very large. Another thing that we learned from here is that our FB, our cutoff frequency, is 10 hertz. So, and we know that omega B should be equals to 2 pi FB. 2 pi into 10 radian per second is our cutoff frequency. So let's find the magnitude response. Excuse me. Let's find the so in the chapter number 1 we find out the transfer function of the low pass filter in the S domain. Do you guys remember what that was? That was something like this, right? So chapter number 1, we find out that the transfer function of a low pass filter was K over 1 plus S over omega naught, where our K was DC gain. This is what we derived the equation, and our omega naught was cutoff frequency. Right? If you, I want you to go back to the chapter number 1 where we were discussing the low pass filters, and we drive down where we drive this equation as well. So if you want to see where this equation was coming from. So once you find out this equation, then you will see that this is also a low pass filter response, this frequency response of the op-amp IC. So I'm going to equate now. Now rather than having a K, we just have a different term, which is A naught. K was a DC gain, and rather than having an omega naught, I just have a different term, omega B. Right. All right, now coming back to this op-amp thing, we have an A naught, omega B. Let's find out the frequency transfer function now. So the transfer function in S domain will be equals to A of S equals to A naught. Rather than K, I'm going to use A naught over 1 plus S over omega B. Similarly, I can also use it as, in terms of J of omega, S equals to J of omega, 1 plus J of omega over omega B. Now let's find out what will happen if... Now interestingly, another thing that we can see over here is if our frequency is very, very larger than omega B, again, omega B was our cutoff frequency. Also looking at the, just excuse me, just by looking at this frequency response, we can also see that as our frequency is increasing beyond omega B or FB here, we have an inverse relationship with the magnitude response with the gain of the amplifier, right? So if omega is very, very larger than all right, so if omega B is very, very larger than omega B, it's an inverse relationship with omega. So we can simplify our equation, and for that condition, so that will become equals to A naught. So if omega is very, very larger than omega B, then our this will become equals to 1 over J of omega over omega B. And we can further simplify it to A naught omega B over J omega. I can also find a magnitude response of this. The magnitude response of this will be equals to A naught omega B over omega. So this is a case when our frequency is very larger than the cutoff frequency. All right, so another thing that we can see from here is our gain value, gain A, reaches unity or mod of A 20 log of 1 equals to 0 dB at omega t. Right, so we wrote another frequency over here which was ft. Ft is a frequency. What is happening at the ft frequency? Ft is the frequency at which our magnitude of the gain is becoming 0, and the magnitude of the gain becomes 0 when our actual gain is 0, because 20 log of 1 is 0. Right, so this is the point, this ft is a point at which our magnitude response becomes unity at ft. So we can also define ft as omega t as 2 pi ft. All right. So our mod of A of J of omega was unity. So this means that omega equals omega t at this point. So if I will replace, if I will use omega equals omega t over here, then omega t becomes equals to A naught omega b. And now we can further put down this equation over here to further simplify a of j of omega, which becomes equals to omega t over j of omega. All right. And similarly in the S domain, a of s, this will become equals to omega t over s. All right. So the interesting thing is that this thing is called as unity gain bandwidth, and I'm going to explain more. Right. So why it is known as the unity gain bandwidth? Okay, so let me do a quick recap by now what we have done. All right, so we looked at the, before coming back, so I'm going to come back to the unity gain bandwidth. By now we have looked at this frequency response. We saw that this frequency response is a low pass filter because of presence of a capacitor. We looked at, interestingly, there are a few things interesting in this plot. One is the cutoff frequency, fb, 2 pi fb is omega b, and this is a frequency at which our magnitude response will start to fall below than 3 decibels or remains within 3 decibels. We also looked at another frequency, ft, but this is a frequency at which our magnitude, the gain magnitude becomes unity, or in decibels it will become 0. We also looked at zero frequency, the DC gain. We found out the DC gain was extremely large. 100 decibels is equivalent to 10 to the 5, 10 to raise to the 5. All right. Then we moved over here. We looked at the transfer function of the magnitude, the transfer function of the frequency response. Over here, this comes out to be this. This is what we have derived in the chapter number 1. So we just made the equivalency here. We saw that when our omega will be very, very larger than the cutoff frequency, then we can, it's a simple inverse relationship, and we can simplify our transfer function to this. And then we define this omega t frequency at which our magnitude gain was equals to 1, which is equivalent to 0 decibels. All right. And finally, with that, we reach to this equation. We reach to this equation, omega t equation, and this equation is interesting because this is what it represents the unity gain bandwidth. Right. So the unity gain bandwidth is the bandwidth of an amplifier, which will have a unity gain. Because omega t over here omega t over here represents the frequency at which amplifier gain becomes unity. So the product of the magnitude response and the omega b is a product. So that product is equals to omega t, which is a unity gain bandwidth over here. Sorry. All right. So last time we were here, a of j of omega equals omega t over j of omega. We can also find the magnitude response of this equation. So if we find the magnitude response of this equation, a of j of omega, this will become equals to omega t over omega. Going back here, right? So this will be omega t of j of omega, and if we find the magnitude response, if we find the modulus of this complex number, if we find the modulus of this complex number, it will be omega t over omega. right? So it will be 2 pi ft over 2 pi f. So it will be ft over f. So an interesting thing that we can see from this equation is, if we know the value of ft, we can find op-amp gain valued at any frequency, right? For example, we know that ft equals 10 to the 6 in our current example, right? So this ft value over here is 10 to the 6. So this means that mod of a of j of omega equals 10 to the 6 over f, right? So for example, if you are interested in finding out the value of a of j of omega at 10 to the 5, 10 to the 4, or let's say 612 hertz, all you need to do is to put down this value. So for example, at 10 to the 5, it will be equals to 10. So you can easily find out the values of the gain of the amplifier if you just know the value of ft. So that's an interesting conclusion that we can draw from here. So this ends our lecture. Let me give you a very quick recap of the lecture again. And in the next lecture, we have one more lecture on the frequency response of a closed loop configuration. And with that, we are going to finish up our chapter number 2. So we're going to discuss that in the next lecture. So let me give you a brief recap, a couple of minutes brief recap of this lecture. So we started with the previous lecture on the difference amplifier. We said that, okay, here is our difference amplifier circuit. We have to reject the common mode gain. These are the conditions. R2 should be equals to R4 and R3 should be equal to R1. In order for the gain to be higher, R1 should be lower, but R1 should be higher to prevent any signal loss. So we said that, okay, inverting, so we came up with the solution of an instrumentation amplifier. Instrumentation amplifier is very simple. It has like it can be divided into two components. The right hand side is like a regular difference amplifier. The left hand side are two voltage follower circuits, non-inverting configuration amplifier circuits that are connected to both the inputs. So they are both non-inverting amplifier configurations. So that is why the gain at both ends of these is simple 1 plus R2 over R1. And we have derived these equations in detail. And then both of these inputs went to the difference amplifier. Our common mode rejection condition was there. And that is why our output was simply equals to R4 over R3 VB minus VA. So we ended up putting down those values to find out this equation for the instrumentation amplifier. Then we started with the frequency response of an op-amp, and that's a very important topic. Ideally, it should be infinite. We know that it cannot be infinite in real world, but it is usually very, very high. Ideally, it should be very, very high at all the frequencies. In real world, it cannot be. So this is the actual frequency response of a typical IC. So that usually its DC gain at 0 frequency is extremely larger. And over here we saw that it is 10 to the 5 or 100 decibels at omega equals to 0. At higher frequencies, the magnitude response starts to drop because it behaves like a low pass filter due to the presence of a capacitor in it. The frequency at which the magnitude response falls by 3 decibels is the cutoff frequency in this case, represented by FB. We also defined another frequency, FT, at which our amplified gain becomes equals to unity. So the product of the DC gain, A0, and FT, at which the gain becomes, and the corner frequency, is the unity gain bandwidth. Is defined as a unity gain bandwidth. So the product of the DC gain and the omega B is known as a unity gain bandwidth product. Sorry. We also defined, yeah, this is, I think we just calculated all the values here. All right, and then we saw that, for example, we ended up deriving this equation, modulus of the frequency magnitude of the transfer function of the op-amp equals omega d over omega, or ft over f. So if you know the ft frequency of any amplifier of the op-amp, then you can find the magnitude response at any other frequency by just dividing it with that in this formula, ft over f. All right, so with that, thank you so much. In the next lecture, we have just one more lecture on the frequency response of the non-inverting configuration. We're going to pick non-inverting configuration as an example and find the frequency response of that. All right, thank you so much. I will talk with you in the next lecture. Bye-bye.